Hello everyone, welcome back. So today we are starting our very first episode in Logistic Regression. Woo! So what is Logistic Regression? It really is a tool that helps computers make decisions like a teacher deciding if a student is going to pass or fail an exam. So we're going to break this down step by step using simple language and really fun examples. So let's get started. I want to start with understanding what classification is, right? Okay, what is classification? Imagine that you have a big basket of fruits, and in the basket of fruits, some are your apples, and then you have some oranges, okay? Okay, so some are apples, some are oranges. And your job is to sort them in two smaller baskets. This is your apple basket, and then this is your orange basket. Okay, never mind. You get the point. I don't have to change the color. Okay, so your job is to really just sort them out. You figure out this is an orange and then it goes here. You figure out, hey, this is an apple and then it goes here. So in machine learning, this is called a classification problem. Instead of just predicting numbers, we want to put them into categories, into baskets. For example, spam detection, right? Is an email a spam or not a spam? Like a medical diagnosis, does a patient have diabetes or not? Or like exam prediction, will a certain student pass this exam or fail this exam? So really, just classification is all about deciding between options. And for the sake of simplicity, we are looking at two options here, our binary classification problems. But most of the concepts we learn will be general for multiple number of classes. But here we want to start with binary, okay? So let's say we want to predict if a student will pass or fail an exam based on the number of hours they studied. Okay, number of hours. And then in Y, we want to predict whether they will pass or fail. And you might be asking, hey, we have our X and Y, and that looks awfully similar to what we did in linear regression. So can we just use linear regression for this? Why do we need a different model? Why are we learning a new concept? Let's go through it and see if we can just use linear regression for this. So let's have a few data points. So I have hours studied, and then outcome, pass or fail, okay? And then 0 means that they failed, and then 1 means that they passed, okay? So 1 hour of study failed, 2 hours of study also fail, 3 also fail, but 5, 6, 7, let's say, pass. So if we try to use linear regression to, okay, let's 1, 2, 3, 4, 5, 6, 7, 0, 1. Then this is going to be here, here, here. This is going to be here, here, here. So if we try to use linear regression to fit a straight line through these points, the line might predict values very weirdly, right? It's my attempt of drawing a straight line, and then it might predict values like for some minutes studied. What if it says, hey, that's negative 0.5. And then for say 9 or 10 hours of study, let's say it says 1.3 instead of just 1. So what does it mean? Can a student be 130% passed compared to just 120% passed? Or can a student be, hey, negative 50% passed? That doesn't really make sense, right? So linear regression gives us continuous numbers. It doesn't restrict our output to just 0 and 1 like we want. That's why we need a different approach, one that turns any number into a probability between 0 and 1. That brings us to our next topic, which is sigmoid function. Sigmoid function, okay? So looking at sigmoid function, think of it for now as this magical converter that just takes any numbers and then always lands you in a spot between 0 and 1, okay? And we're going to look at the math later, but for now, just humor me for now, okay? Sigma z e to the power negative z. And what is our z? We know our z is just, it comes from our linear equation, okay? So let's break this down. Why this function always gives us an answer between 0 and 1. So if we have a positive exponential, then no matter what z is, no matter what this is, will always be positive. That means e to the power negative z will always be greater than 0. I realized that I forgot to provide an intuition for why e to the power negative z is always 0. Sorry, is always positive. Sorry, not always 0. Oh my god, okay. Why? I don't know if you remember from your calc days, but this is what your e to the power x looks like, right? So if the e to the power x looks like that, then when you mirror it, this is what your e to the power negative x should look like. Now, no matter how much you stretch that, no matter how far you go, it will never touch 0. So what we see here for both of these, they are always greater than the 0 line, right? They're always up from the 0 line. That's why e to the power negative x, no matter what the value of x is always positive. And just looking at this graph, the intuition for understanding the extreme value should be a bit clearer too. So I just wanted to jump in and clarify this. Now back to the original video. And the denominator is always larger than 1, right? If this is already greater than 0, then that means the denominator is always larger than 1. And now, what happens when the denominator is always larger than 1? The function takes 1 divided by a number that's always more than 1. So the result is always less than 1, but greater than 0, okay? So we have 1 plus some positive number. So the result here will always be, the result here will always be between 0 and 1 for our sigmoid function. And then let's look at the extremes as well, right? So when z is just a very large positive number, then in that case, our e to the power negative z becomes 0. So what happens when this is 0? Let's just fill it out. Okay, 1 plus 0. What is 1 divided by 1? It's just 1, right? And then when our z is a very large negative number, right? Then at that point, e to the power negative z becomes huge. So this will look like 1 by 1 plus like a huge number, right? What is 1 divided by 1 plus 1? 1 plus a huge number. It's going to be closer to 0. So that means no matter what, the sigmoid function's output is always safely between 0 and 1. This is why it's really perfect for converting our linear model's output into a probability that tells us, yes, the student will pass, or no, the student will fail. And the sigmoid curve looks something like this, okay? I'm doing this, and then this is my 0, this is my 1. I'm just going to have, okay? And then it's going to look something like this. So it's always going to land between 0 and 1, okay? Sorry, I got stopped. Okay, let's go back. So, okay, it's always going to land between 0 and 1. But if we had our straight line, best fit line from our linear regression, what do we know? It could be something like this. So it could easily exceed values beyond 0 and 1, not really giving us the probability that we need, okay? So now turning probability into decisions. Now we look at what's called a decision boundary. Once we have these probabilities from sigmoid function, we need to make a final decision, right? So we do this by choosing a threshold, and the common threshold is just your 0.5. So if the probability is higher than 0.5, then classify it as 1, which is pass. If it is less than 0.5, among the higher or equal to less than 0.5, we classify it as fail, which is just your 0, right? So this threshold creates a decision boundary, which is like drawing a line that separates the two groups. Imagine just drawing a line in a playground, and students on one side are in the team pass, and then those who land on the other side are in the team fail. That's exactly what logistic regression does. And in terms of real-world application for logistic regression, it's used in so many real-life problems. Let's just look at a few. So in healthcare, doctors could use logistic regression to predict if a patient has a certain disease based on factors such as age, blood pressure, cholesterol levels, right? In finance, banks could use it to decide if a loan applicant is likely to default. Likewise, let's say in marketing, companies could use it to predict if a customer will buy a certain product or not, just based on their past buying behavior. And then in education, schools might just predict if a student will pass an exam based on study hours and attendance. So these examples just sort of show how logistic regression is a very versatile tool for making decisions, where the outcomes are those yes and no questions. So let's quickly recap what we learned today. We learned what classification is, which simply means sorting things into groups like pass, fail, span, not span. Linear regression fails for classifications because it can output impossible numbers, like we looked at our 1.3 and negative 0.5. The sigmoid function is our magic tool that converts any number into a probability between 0 and 1. We use decision boundary, which is usually 0.5 to classify predictions as 0 or 1. And then logistic regression, sorry, logistic regression is, I'm just out of breath because I've been talking a lot today. Logistic regression is used in many areas like healthcare, finance, and education. So in our next episode, we will dive deeper into the math behind logistic regression, exploring the cost function, how we train the model using gradient descent, and more advanced topics. So be sure to like, subscribe, and just follow along so that you don't miss out on the next deep dive. See you soon.